Hi there, everybody. This is Mike Laurendeau, the Eastern US and Canada Product Sales and OEM Accounts Manager for Caron Engineering. First and foremost, I want to thank you for giving me 30 minutes of your time today. I know your time is valuable and I appreciate it. I'm here to present Defeating Machining Challenges webinar number 2 with a focus on TMAC 3.0. First, I want to start with identifying some machining challenges. Number 1. Variations in material, your tooling, and your depth of cut plague machining. 2. Determining your condition of your tools and maximizing your tool life are of utmost concern. Number 3. Reduced reliability of skilled workers and relying heavily on unattended operations. We all know the difficulty with our labor force, specifically at the operator level. I have seen more and more robots in the last 2 years than one could imagine. This isn't going away. So what's next in our current climate? The lowest entry point cost-wise to satisfy orders is for customers to optimize their current equipment. So what I want to do is introduce the solution to all of these problems. That solution is TMAC. TMAC stands for Tool Monitoring Adaptive Control. In this slide, we're going to evaluate the tool monitoring aspect. TMAC measures tool wear in real time. It utilizes a high-resolution sensor to determine if a tool is worn or broken. We prevent breakage and reduce scrap rate by setting accurate limits around each tool and each cut. TMAC provides an enormous amount of valuable information about your cutting process. And finally, it eliminates the need for operator intervention. So here with our adaptive control, we automatically regulate your feed rate through variations in your material, your depth of cut, and your tooling. It's going to optimize cutting and reduce your cycle time and allow unattended lights out operation. Adaptive also reduces the cost of consumable tooling by increasing your tool life. We do this by making 1% increment changes in your feed rate in order to actually react to harder and softer material condition. So here's a pretty standard example of our system components with TMAC. First, we have a sensor connected to our high-speed processor. The sensor is an auto-scaling Hall effect transducer. It's mounted in your electrical cabinet between the spindle and the drive. This measures true motor horsepower. Next, we have our high-speed processor. This is a dedicated Linux-based system that's installed in the machine cabinet. This connects your sensor to your CNC control. It's important to note that CNC controls only allow a small amount of processing power. That's why we use our own system. It also allows instantaneous reaction to conditions with real-time machine interfacing. The third part of our system is our browser-based HMI. The TMAC processor houses its own web server to allow remote real-time monitoring from any network device. This is also entirely configurable to different password-protected interaction from supervisor to operator levels. Here we have some sensor options: power, vibration, strain or a micro tool sensor. We can monitor coolant, flow, pressure, and spindle speed. All of the sensors can be used by TMAC to react to anomalies in the normal machining operation. We also can take a 0 to 10 volt or 4 to 20 milliamp input as well for sensors that we don't commonly support. Here, TMAC monitors multiple processes and sensor channels simultaneously. On this particular graphic, you can see the 4 quadrants of horsepower, vibration, spindle speed, and coolant. TMAC cannot be overloaded by any of these, and it's fully capable of monitoring all of those simultaneously and more. So TMAC first learns the cut. The screen turns green and we actually grab the peak horsepower value of each tool in each cut. TMAC learns that peak power, it latches onto that peak power, and then when you're actually in monitoring mode, it automatically scales the display to the ideal monitoring range. So how does it work? TMAC uses different monitoring modes based on the specific operations being monitored. So we have fixed limits, work, and adaptive control in our toolbox. TMAC learns the peak power and area under the curve, or work, of the cutting tool and can detect tool wear by monitoring these parameters. Here we have our adaptive control. Without adaptive, a constant feed rate is set based on the safest or worst material condition. With adaptive, TMAC learns the optimal power and automatically adjusts that feed rate based on the load. So what's the result? Decreased cycle time, longer cutter life, and more machine uptime, especially with difficult to handle materials. With our new browser-based UI, you can access TMAC anytime, anywhere, and from any network connected device. By using a vibration sensor attached to the spindle, TMAC can monitor spindle bearing health. So what we do is we put a low mass tool in the spindle, we ramp that spindle up to its highest RPM, and we do a 5-second analysis of acceleration and velocity. And you have now access to your spindle being in good condition, on its way out, or bad. All of this data can be trended over time and networked to your maintenance department so they can have those data files at a glance. Finally, we have a TMAC event viewer. All these monitored data and events are stored and can be exported in different formats. So you can also add filters, columns, and other customizable views. So you simply can click on any event and view those details. So now let's go check out our on-machine demo. What we have in the background, folks, is our TMAC 3.0 system running. In the upper right-hand corner, you see the webcam of the inside of this 3-axis mill that we're running our demo on today. So this is a 1mm drill. 1, 2, and 3. Also, it's important to note that down below, we're actually also measuring the vibration. We have a vibration sensor mounted in the machine as well. And we're coming up with a 10-30-second drill. You'll see the start command come in, long vertical line, and we have limit set. So here we're measuring these drills, these holes, using area under the curve. Once again, the blue is the satisfaction of the undercut. So we're saying enough power was consumed to satisfy that that drill is there. Next tool is a 1/4-20 tap. This is simply tapping the 10-30-second drill. Now you're going to see the screen actually flash a couple of different colors. The gray basically means we're doing a monitor hold. So in a tap sequence, and this is unique to us, in a tap sequence, you're going to capture a spike in power on the reversal of the spindle. So we actually ignore all of that and just capture the actual forward cutting of that tap. And we can set those parameters. So that's kind of what you're seeing in the screen there. And then finally, we're going to come in with that 1/2-inch 2-flute end mill. Full depth of cut on the first pass. Now this is an adaptive cut. So we are going to see the variation in the feed rate based on the amount of power being achieved by the tool. So that inverse relationship is represented there on the top of your screen. It's also interesting to note that the vibration signature follows the horsepower signature really closely, which is interesting. Now next cut is a 1/2 depth of cut, essentially cleaning up the first pass, if you will. So we're satisfying that blue, saying enough undercut was met. That essentially will start to turn green, saying we're satisfying the cut. And if it were to get to a point where we're achieving more power and getting into a wear condition, where that would then shade yellow. It's the final cut. And this is just cleaning it right up, the whole phase. And finally, we're doing a bearing analysis for you. We ramp the spindle up to its highest RPM in a low mass tool, take that 5-second sample, and do the analysis of acceleration and velocity. And you'll see the end result here in a moment. And we do know that the velocity that our spindle is actually not that healthy. So I'm going to maneuver through how to get around TMAC 3.0. First of all, on the top right part of the screen, there's the label of the machine. It could be machine number, whatever you want it to be, job, mode, or status, and if it's in an alarm state. Up here, we actually have the ability to do permissions for operator level, supervisor level, integrator level, depending on the situation, to password protect, and we can permit them to do certain functions of interacting with TMAC. So I'm going to show you down here at the bottom, we got power, vibration. Well, you can basically create custom screens to show all of these things happening simultaneously if you prefer. Here on the left column, we have job, enable learn to turn a learn on manually, reset, mode functionality, event log, viewer, and system. So in the job, this is where you interact with your jobs. So TMAC is job-based. So once you learn a PAR program, it's saved. This would be how you interact with it. So I'm going to edit active job and show you the current job that we just monitored. Tool 2, Tool 3, Tool 4, Tool 5. These are also represented by sections. So on Tool 5, we're actually doing 3 different operations. Okay. The first was that full depth cut with adaptive, as you can see here by this radio button being selected. Tool 2, here's an example where we're using basically fixed limits. If you wanted to turn area under the curve on, you just would simply click that to turn the work calculation on. So these are the different channels down here on the left: power, PSI, vibration. This is where you essentially set it all up. This is where you set your parameters. So we learned this value here in the learn parameters, the horsepower, peak power achieved. And then this is where you set your alarm states. There's also filter options and whatnot. It's important to note with adaptive that we can also do things like turn approach on and off, and that was that rate of change calculation I was telling you about. But we also can tell adaptive to speed up a certain amount, traditionally up to 255% of the program fee rate, but also slow it down if need be. So it really is a tool that can be used for multiple applications. I also wanted to show you our viewer function. So what viewer does is it pulls up an additional browser, just pulling it up here. And I want to we can do an analysis of bearing health, millivolt, or cutting. I want to look at cutting. So what I'm going to do is this pulls up the most recent cut, right? You can scale back and forth, previous, next. I want to show you the power of being able to analyze a tool, for example. I'll remove this. These are all the recordings of every tool that we've been monitoring and actually learning. I'm going to add a filter, and I'm going to pull up tool 5, which is that half-inch end mill. And I want to do an analysis of when we learned it at 100% feed rate, and when we turned adaptive on up to 150% feed rate override, and do a quick analysis to see how much time we saved. So I'm going to pull up the learn file first. So I'm just adding a filter, tool 5. And I'll apply that. And I'll just pull the most recent one, and that just happened. It's all time and date stamped. And then I'm just going to pull up the monitor version of that same tool. It's also important to note tool 5, T5, S3, that's the tool and section. There's also a motor designation too if we were using a multitasking machine. Pull this monitor. So now I've got these two. I'm going to hit apply. Now they're overlaid on top of each other, so I can toggle between the two and show you that on the learned one, I'm going to pull up the details. We have details to show cursor, where you were, events as well. This duration on this particular cut took, well, almost 30 seconds. Now with the adaptive cut, we actually are seeing the duration of 21.09 seconds. So we shaved about 9 seconds off of this tool using adaptive. Another analysis you can do, you can pan, click, zoom. So
wherever you are with the cursor, we satisfied at the undercut, for example. We're going to show things like your limits, what percentage you would satisfy, the power, the relative power, but also passive details like axis position in the machine. Or we can zoom in. Maybe I want to look at this area here. I draw a box and it zooms in, and I can continue to zoom in.
So I want to kind of recap what you've seen here today with TMAC. TMAC is a real-time machine monitoring and optimization product. It automates processes and allows unattended operation with confidence. All the data is accessible anytime, anywhere, and from any device. It interfaces with almost any CNC control, and it maximizes your tool life. It adapts to changing material, your cutting conditions, and your tooling. TMAC makes automatic corrective adjustments on the fly. And finally, it has a multi-process monitoring capability. So now you can monitor everything that's happening in the cutting environment. In addition to these features and capabilities, we also provide local support via our integrator network. Caron Engineering is based in the United States, and we are made in the United States. Finally, I want to introduce you to our next webinar series, series number 3. We'll be demonstrating how our Tool Connect system uses RFID technology and easily integrates with a tool presetter to automate and optimize the tool load process. I want to thank you again for your time today. If you have any questions or comments, please email us at marketing@caroneng.com. Once again, marketing@caroneng.com. Thanks and have a nice day.